All right, welcome to the Explainer. Today, we're pulling back the curtain on advanced cryptography. You know, all that invisible stuff that's working hard in the background to keep your entire digital life private and secure. It's like this invisible shield that's with you every single second you're online.
So, here's what we're going to cover. First, we'll talk about the fundamental problem, this crisis of trust online. Then, we'll look at the solution, building secure tunnels with something called TLS. After that, we're going to peek inside that tunnel to see how your data actually gets encrypted. Then, we'll get into how we prove who's who online with digital passports. And finally, we'll see where this tech pops up in your everyday life.
You know, before we can even talk about securing the internet, you've got to understand its core challenge. See, it was originally built for openness and sharing, not for keeping secrets. And that created a huge problem.
And that right there, that's the big question. That's the crisis of trust the internet's pioneers had to solve. Any message, any piece of data you sent out could be intercepted. It could be read, or worse, it could be changed. And just as big a deal, anyone could pretend to be someone they're not.
This quote just hits the nail on the head. It frames the problem perfectly. You've got two huge issues here. You need confidentiality, that's keeping your data secret, but you also desperately need authentication. That's proving you are who you say you are. If you don't have both, secure communication is basically impossible. So how in the world do we solve this? Well, the answer starts with this really brilliant idea. What if we could create a secure, private tunnel that just cuts right through the public, insecure internet? The first crack at this was back in the mid-90s with something called SSL, or Secure Sockets Layer. The idea was revolutionary for its time. Just wrap all communication in this protective, encrypted layer. But as is often the case with version 1.0, it had some serious vulnerabilities, and, well, it needed to get better. Fast. And get better it did. That evolution led us to TLS, or Transport Layer Security. This is the powerhouse protocol that pretty much underpins the entire secure internet we use today. It's the reason you see that little lock icon in your browser's address bar.
So how does it work? Well, you can think of it in three main steps. First, your browser and the server do a little handshake, where they introduce themselves and agree on the rules for encryption. Next, they do a super secure exchange of cryptographic keys. And then finally, they use those brand new keys to build that encrypted, secure tunnel for all the rest of your data to travel through.
Okay, so we've built the tunnel. Awesome. But what's happening inside that tunnel? How is your data actually getting scrambled into total gibberish? This is where the real magic happens, and it's way more powerful than a simple little substitution cipher.
See, instead of encrypting data one letter at a time, modern systems use what are called block ciphers. They take your data and chop it up into fixed-size chunks, or blocks, and then encrypt each block. The mode of operation is really just the instruction manual, the set of rules for how to handle all those different blocks to make them secure.
One of the earliest methods had a really simple analogy. Imagine you have a top-secret codebook. For every unique chunk of your original data, you just find its matching secret code word in the book. It's simple, it's direct.
But there was a huge flaw in that simple codebook method. It was dangerously predictable. If you sent the same block of data twice, you'd get the exact same encrypted block twice. And for anyone trying to break your code, spotting patterns is step one. So modern modes fix this by adding a bit of, well, chaos. They add randomization, making sure that even if you send the same data 100 times, it looks completely different every single time it gets encrypted. No patterns, no clues.
Okay, a secure tunnel is fantastic, but it's pretty useless if you don't really know who's on the other end. I mean, you could have a perfectly secure tunnel that leads straight to an imposter server. And that is where digital certificates come into play.
Think of it exactly like your passport. A digital certificate is an official document that ties a specific identity, like, say, Google.com, to its public encryption key. It's the proof that says, yes, this public key really belongs to Google, and you can trust that you're talking to the real deal.
In fact, if you ever click on that little lock icon in your browser and look at a site's certificate, you're basically checking its digital passport. You'll see who issued it, kind of like the government that issued the passport. You'll see its expiration date, the type of encryption it uses, and a unique serial number to make sure it can't be forged.
So, how do we know we can trust the issuer of the passport? Well, it's because your computer's operating system and your browser come with a pre-installed list of these major, highly vetted certificate authorities. They are the root of trust, and they're the ones who vouch for the millions of websites you visit, creating this unbreakable chain of trust all the way down to you.
All right, let's bring this all home. How do all these pretty complex ideas, these secure tunnels, block ciphers, digital passports, how do they actually show up in your day-to-day life?
Well, it is everywhere. Every time you see that S in HTTPS and the little lock icon, that's it. Every single time you use your credit card online, it's working to protect you. It's verifying that the software update you're about to install is legit. It's protecting your emails as they travel across the globe. It's creating the secure connection for your VPN. It is constantly at work.
So the one thing you really should take away from all this is that online security isn't just one magic bullet. It's a powerful, layered system. It's a team effort. You've got the tunnel from TLS, the scrambled data from the block ciphers, and the identity check from the certificates. They all have to work together perfectly. If you take away even one of those layers, the whole structure of online security as we know it would just crumble.
If you enjoyed this deep dive and want to learn more, make sure you follow the Firewall Support Center on YouTube. Thanks for watching.